Okay, so now we're here. All right, so I redrew Mohr's circle. I erased some of the stuff that I had done previously in the principal stress state, and I just started with what we need. Okay, and here I have, again, I just drew a point A here. I have the radius calculated here. R equals 3.35 KSI from the previous part. And then alpha was calculated, this angle here was 63.4 degrees. Okay, all calculated previously in that part 2 video. And now what we want to do is get the maximum in-plane shear stress. And the maximum in-plane shear stress is literally the furthest we can go out from the circle in the plus tau direction, in the shear stress direction. So in this case right here, the maximum in-plane shear stress is right here. This is, if you will, my lowest point right here. Okay, and this distance is the radius. Okay, so my tau max right here, tau max is just equal to the radius, which is 3.35 KSI. Okay, at this point right here. So here is my max in-plane shear stress state right here. There's my 3.35 KSI. The angle it takes me to get to here, this line, if you will, this line, the angle for this line right here is alpha plus 90 degrees. Okay, so this angle, this new angle that for me to go all the way over here, which I will call, oh, I don't know, shoot, let's just call it beta. Okay, call it beta again. Okay, so beta, this, let's not call it beta, let's call it phi. This angle phi is equal to beta, or alpha, plus 90 degrees, which in this case is 153.4 degrees. And now if I want to know, so this is my angle I need to rotate clockwise in Mohr's circle. And so in real life, the angle theta s would just be phi divided by 2, which is 153 divided by 4 is 76.7 degrees clockwise in real life for all my representative volume element. Okay, and so here, this point right here, now if I want to draw, I know my stress, I know this point right here, the coordinates of that point. What are the coordinates of that point? The coordinates of this point are minus 0.5 KSI, comma, 3.35 KSI. Okay, and now I want to draw the state of stress here. And so again, I start with my a horizontal line. Horizontal line here. Let me get some space here. So I start with the horizontal line, my reference from theta equals 0 degrees. There's my reference right here. And then I'm going to go 76.7 degrees, which is a pretty big angle. So here it's right here, 76.7 degrees, this angle. Call this 76.7 degrees. Is that right? What we had before? 76.7, yes. Okay. And now I draw, at that point, I draw a line perpendicular to this line right here. So perpendicular to this line, I draw right here, like this, and then I complete my square. Okay. Complete my square, as messed up as it may look. Okay, or my rectangle, whatever. My represent completing it. Okay. It's all a bunch of 90-degree angles. It's a no-brainer. Okay. So that looks pretty good. Okay, it's close enough. Whatever. All right. This is, if you will, my new, okay, plus x direction, or new direction right here, 76.7. Okay, and here on this face, representing this right here, I have a normal stress of minus 0.5 KSI, which means, okay, my coordinates of that face are minus 0.5 and 3.35 KSI, which means here I have 0.5 KSI causing compression right there. Okay, here's my new plus x face, if you will, x prime, and here the y just comes along for the ride right here. Here's my plus y prime. Okay, y comes along for the ride, x is what's rotated, and this angle, this right here, my shear stress is positive 3.35. That means here on my plus x face in my plus y direction, which is here, plus x face in the plus y direction, and then I complete this rest of the shear stress that's based on equilibrium. Okay, bam, 3.35 KSI KSI, and then here I have here equal and opposite 0.5 KSI causing compression. And then I have to think about what's my normal stresses here. And just like we were talking about before, to go from x prime to y prime here, it's a 90-degree rotation in Mohr circle, right? Counterclockwise or counterclockwise to get this way. So that means it would be 180, 90-degree rotation in the representative volume element. It'd be 180 in real life. That means I'm all the way over here. And hey, my normal stress here is also 0.5 KSI, negative. So here, bam, 0.5 KSI, 0.5 K, and this right here is my solution to the maximum in-plane shear stress state. If you give one angle relative to the horizontal and you draw all the stress states, all the normal stresses, all the shear stresses, you're good. You're done. That's the solution. Doesn't matter how you get it. All right. Hopefully that was helpful. Let me know if you got any questions. Laters.